This is R5 Rational Expressions, Day 1. Before we get started, let's review factoring a little bit. When you are factoring any problem, one of the most important things to remember to do is always look for a GCF first. And that's where some people get into a little bit of trouble because they forget to look for a GCF. So just want to reiterate how important that is. We want to look for a GCF first, which this one has. So we want to take the x out, leaving 81x squared minus 4. Now when we look at that, we can see it's a binomial, so we're not going to be doing splitting the middle. We're not going to be doing factoring by grouping, but we can use our difference of squares because 81 is a perfect square, x squared is a perfect square, and so is 4. So we can take the square root. The x that we took out originally still stays on the outside. Square root of 81 is 9. Square root of x squared is x. And then square root of 4 is 2. So we have 9x minus 2. And if you remember the pattern, we would also have that multiplied times 9x plus 2. All right, let's get into rational expressions. Rational means can be written as a fraction, so you'll see that here. And we are essentially going to be continuing with our factoring. That's why those previous sections were so important, because we are going to be factoring both the numerator and the denominator. So if we look at our numerator, we want to check for a GCF. It has one. We can factor out a 2. And do the same thing on the denominator. Check for a GCF. In this case, it's 3x. Now you'll notice that both in the numerator and the denominator, we have an x plus 5. Well, if you take anything and divide it by itself, it equals 1. So x plus 5 divided by x plus 5 equals 1. So we can divide those out to equal 1. 2 times 1 is just 2, so we're left with a 2 in our numerator and a 3x in our denominator. Now the other piece to this is that we don't want, if you might remember from the past, we don't want a fraction to have a denominator of 0. So we can't divide by 0. And some values, when you put them in, would make our denominator equal 0. We want to exclude those values. So when you take this x plus 5 out, if we had put a negative 5 in here, negative 5 plus 5 would have given us 0. 0 times 3x would have given us 0. So negative 5 would have been a bad value for our fraction here. It would have made our denominator equal 0. So we want to say x cannot be negative 5. Now some of you might be thinking, well, 0 would make our denominator 0 as well. 3 times 0 is 0. Do we need to write 0 here? And the short answer is no, because it's still obvious in the final answer. In this final answer, we can see that we can't have a denominator of 0. But since we removed these x plus 5s, we can't see that negative 5 was not good in our original. So we have to state that we can't use x as negative 5. So that's restricting our domain there is what we're doing. And we'll go over it many times. But so we need to factor to simplify and then decide if there's anything we need to restrict for our domain. All right, so here's our next one. What I want you to do is pause the video, write it down, and go ahead and try to factor it. This one's going to factor a little differently than number 1. Instead of just GCFs, you're going to be actually finding what multiplies and what adds. So go ahead and pause it and give it a try. All right, so our numerator, hopefully you factored that to x plus 5, x minus 2. We had to find things that multiplied to negative 10 and added to 3. So multiplying to negative 10 would be negative 5 and 2, and those, I'm sorry, positive 5 and negative 2. I flipped those. Positive 5 and negative 2, and then they add together to get 3. Likewise, on the bottom should be x plus 7 and x minus 2. Like we saw in number 1, we have some things in our numerator and denominator that are the same. When they divide out, they're going to equal 1. So now we're left with x plus 5 in our numerator and x plus 7 in our denominator. Since we took out the x minus 2, it's no longer obvious that that was a part of our original denominator. So we need to make sure that we exclude the number that would make it equal 0. And 2 minus 2 would make it equal 0. So we're going to take out the 2. Restrict that part of our domain. All right, we're going to continue just doing the same thing. Here's another example. I want you to pause the video, write it down, give it a try on your own, and then come back and check. Trying it on your own is essential for you to understand these, so definitely please pause and give it a try. All right, the top is kind of like our warm-up. It's a difference of squares. That factors to x minus 4, x plus 4. And then our denominator, we take out a GCF to start. 4x goes into both of them, and then we're left with x minus 4. So we can see an x minus 4 in our numerator and an x minus 4 in our denominator. So we can divide those out. They equal 1. And we're left with x plus 4 in our numerator and 4x in our denominator. Now some people ask here, can we simplify the 4's or can we simplify the x's? Even up here on this one, sometimes people ask if they can simplify these x's. You cannot simplify if things are being added or subtracted. You can only simplify when things are being multiplied or divided. So here, the reason why we could take out these x minus 4's is because they're being multiplied by these other things. We cannot take away this x. This x is connected to this 4. If it was being multiplied by the 4, different story. But if it's being added or subtracted to the 4, you have to leave it. They're a family. You cannot separate them when they're being added or subtracted. And so that's all one group that has to stay together. But are there any numbers that we need to make sure x cannot be? Well, we took out x minus 4, so 4 would have made it equal to 0. So x cannot be 4. All right, here's our last one. Go ahead and write it down, give it a try to factor it, and then come back and see how you did. All right, the numerator on this one is like the last one, a difference of squares. So hopefully you noticed it was x minus 5, x plus 5. Now this next denominator, you can look at in a couple different ways. I like to look at all of my polynomials when they're written in standard form. What I mean by that, these are written backwards to me. Remember when we write things going from greatest to least of exponents? So this really should be negative 2x plus 10. The negative goes with the 2, the 10 is positive. So I'm going to use it this way. And I'm first going to look for a GCF. So it looks like negative 2 is our GCF. Okay, so negative 2 would leave an x minus 5. Now, depending on how you factored it, if you didn't switch it around, maybe you just took out 2 as a GCF. So then you had 5 minus x. 5 minus x and x minus 5 are not the same. And that is why you can get into some trouble if you don't rewrite it into standard form. The reason they're not the same, just in case you can't see that, this 5 minus x, let's rewrite it so that it's written the correct way with the x first. Notice that it is a negative x plus 5, whereas this one is a positive x minus 5. Completely opposite. Now the other option you have is after you do this, you could take a negative out of both of them to get x minus 5. And now these two match. But to me, that's extra work. And if you would just write it in standard form from the beginning, that could really help. All right, so let's go back to where we were. We have an x minus 5 in our numerator and our denominator. They divide out to equal 1. We're left with x plus 5 on top and negative 2 down below. We took out an x minus 5, so that means x cannot equal 5. And we don't even have any x's left in the denominator here, so that's very not obvious, so it's a good thing that we need to state it. When we get to graphing, you'll see that these numbers that we're taking out become something called an asymptote, or a place on the graph that your lines, your function can't touch. We'll get to that later.